Hello guys, welcome back to a brand new video. Today we're going to be learning about Introduction to Radioactivity. Radioactivity is the fundamental process in nature involving the spontaneous emissions of energy and particles from the nuclei of unstable atoms. This phenomena has been studied extensively and had led to numerous important applications in science, medicine, and industry. In this presentation, we will explore the fascinating world of radioactivity from its atomic origins to its diverse uses and impact on society. Before I start the video, make sure you check our channel for more videos like these. And yeah, let's begin. Atomic structure and radioactivity decay. Atomic structure. All matter is composed of atoms, which consist of dense, positively charged nucleus surrounded by a cloud of negatively charged electrons. The nucleus is made up of protons and neutrons, and the combination of these subatomic particles determines the elements and its properties. Radioactive decay. Some atomic nuclei are unstable and undergo process known as radioactive decay, where they emit radiation in the form of particles or energy to reach a more stable configuration. This process is spontaneous and random. The rate at which it occurs is unique to each radioactive isotope. Nuclear forces. The strong nuclear force which holds the protons and neutrons together in the nucleus is what gives atoms their stability. However, in some cases, this force is not strong enough to overcome the repulsive forces between the protons, leading to a radioactive decay. On the right, you can see the diagram with electrons, neutrons, proton, and nucleus. Types of radioactive decay. Alpha decay. This type of decay, the atomic nucleus emits an alpha particle, which is a helium nucleus, 2 protons and 2 neutrons. Alpha decay is typically observed in heavy unstable elements such as uranium and radium. Beta decay occurs when a neutron is in the nucleus is converted into a proton, an electron, and an antineutrino. This process can result in either the emission of a negatively charged beta particle electron or a positively charged beta particle positron. Gamma decay. Gamma decay involves the emission of high-energy electromagnetic radiation known as gamma rays from the nucleus. This type of decay often follows other forms of radioactive decay as the nucleus seeks to reach a more stable energy state. Radioactive half-life. Definition. The radioactive half-life is the time it takes for a radioactive substance to lose half of its original activity or mass. This is a fundamental property of each radioactive isotope and is used to predict the rate of decay and the remaining activity of a sample. Measurement. Radioactive half-life can be measured by observing by the decreasing activity of a sample over time. This is typically done using radiation detectors such as Geiger counters or scintillation detectors. which measures the number of radioactive decay events per unit of time. Applications. The concept of radioactive half-life is crucial for many applications, including dating geological and archaeological examples, determining the age of the Earth, and calculating the safe handling and storage of radioactive materials. Radioactive isotopes and their applications. Medical applications. Radioactive isotopes such as tritium 99M and iodine 131 play a vital role in medical imaging, diagnosis, and treatment. They are used in techniques like positron emissions, tomography, PET, and single photon emission, computed tomography, SPECT, to visualize internal organs and identify diseases. Industrial applications. Radioactive isotopes have numerous industrial applications, including radiography for inspecting materials, gauging the thickness of materials, and tracking the flow of fluids in industrial processes. They are also used in smoke detectors and as a power sources for satellites and spacecrafts. Research applications. Radioactive isotopes are essential tools in scientific research, enabling the study of chemical and biological processes, the dating of archaeological and geological samples, and the investigation of the structure and properties of the same materials at the atomic level. Environmental applications. Radioactive isotopes can be used to monitor and study environmental processes such as tracking the movement of pollutants, measuring the age and flow of groundwater, and determining the source of contaminants in soil and water. Radiation measurement and units. Activity. The rate of radioactive decay measured in becquerels, BQ, or CI. Dose. The amount of radiation absorbed by a person or material measured in GY or rads. Exposure. The amount of radiation a person or material is subjected to, measured in SV or R. Shielding. The use of materials such as lead or concrete to absorb or block radiation and protect people or equipment. Biological effects of radiation. Ionization. Radiation can ionize atoms and molecules in living tissues, damaging DNA and disrupting cellular processes. Cell damage. Ionizing radiation can cause cell death, chromosome abnormalities, and mutations, leading to various health effects. Biological effects. Exposure to radiation can result in acute radiation syndrome, increased cancer risk, and genetic effects depending on the dose and exposure duration. Radiation protection and safety. Time principles: time, distance, shielding, alara. Description: minimizing the duration of radiation exposure, increasing the distance from the radiation source, using appropriate materials to block or absorb the radiation, keeping radiation exposure as low as reasonably achievable. The fundamental principles of radiation protection guide the safe handling, storage, and use of radioactive materials to minimize the risk to workers, the public, and the environment. Nuclear fission and fusion. Thank you guys for watching. Make sure you like and subscribe, and make sure you check our channel for more videos like these, and I'll see you guys next time.